So hi everyone, my name is Urvin and today I'm making this video to demonstrate my task 6.3 HD of networks and communication. So here we are going to discuss about the protocol QUIC, which is the Quick UDP Interconnection Protocol, Internet Connection Protocol. So in this video we'll discuss what is QUIC and then why we need it, what are the functionalities, what are the frames of the QUIC advantages, and then applications, and then check if we are having any security threats and if it is scalable or not. So let's begin with our video. So QUIC is a general purpose transport layer protocol which is built on the top of UDP, and it was originally designed by Jim Roskind at Google in 2012. So earlier it was deployed widely then across by Google services by 2013. Nowadays it is used in every single application like YouTube, Gmail, gaming, and etc. etc. So it was then standardized by the IETF in May 2021 as the RFC 9000. So why we needed the QUIC? Because initially, let's compare the TCP because it is more reliable because it has an inbuilt TLS version 1.3 and also it has short round trip times. And not only this, we'll also compare why it is better than TCP, why there was a need to establish such protocol. So let's begin. So the first point is talking about the head of the line blocking. So it usually occurs in the TCP, but not in the QUIC. Why? Because if we are sending 1 to 5 packets from a client to a server, then if somehow the third packet is being lost, then what will happen is the client will be acknowledged that the server has been sent with only the two up to two packets and will neglect the other fourth and fifth packet. So it will say that I have received only up to two. But in general, we have also the TCP connection has also sent the fourth and fifth packet, and hence there will be data duplication and it is really unreliable. But in the terms of QUIC, it uses the SAC, which is the SA acknowledgement, SACK, which is in the SAC, it acknowledges about what packets are received. In terms of QUIC, it will tell I have received this number of packets. I have received 1, 2, 4, and 5 packet, but not the third one. So only the third one will be replied back, which eliminates the duplicacy as well. But talking about the head of the line blocking, if in terms of TCP, it is usually observed that if the packet is lost, then the next packets are being waited before the that package is being resent. So it causes head of the line blocking, which causes a lot of delay. But there is no delay in terms of QUIC because it sends a particular packet using the SAC. And also, we'll be discussing about the frames, which will tell us about the function of multiplexing and why there is no head of the line blocking as well. So another drawback of TCP is that it requires a high handshake latency because TCP uses a three-way handshake for TCP communication and then another handshake for the TLS. So this delays the data flow. And other fault is that there is no connection migration because if a TCP connection is tied to a particular IP, and if that device IP is being changed, then the whole network data, whole path will be changed, which is another drawback. So so the another drawback is the kernel ossification because if we want to improve the TCP, then we have to change settings in our OS kernel across millions of servers, which is really difficult. So we can easily so for that we had implemented QUIC protocol, which is implemented on the user application only on the user side. So it is really easy, and hence we have improved that over the TCP. So as you are already familiar about the TCP header segment, so it contains source port, destination port, and sequence number, acknowledgement number, and so on. So these are the headers inside the TCP. We are already acknowledged by them. So for the hands-on Wireshark analysis, I would like to show the current IP of my machine. So for the IPv4 address, my machine's IPv4 address is 192.168.146.158. So remember this IP, and we'll compare it with the other packets of QUIC and TCP. Okay, so another thing I noticed that I am using the DHCP protocol, which is providing me a lease of one day. So after that day, my IP will be changed. So we can see that if we are using the TCP, the whole migration will establish again. We have to use different IP address, and then we have to look at all the pass through all the routers, which will cause delay. So before going to Wireshark, I would like to discuss about the frames and formats of QUIC packet. So there are different types of frames, which are first is the crypto frame, which carries the TLS1 version 1.3 certificates for the handshake process, and then we have the stream frame, which will carry different stream IDs for a particular which will carry different stream ID for particular data, and then we have the acknowledgement with SAC inbuilt, which will tell if there is any loss, then a particular acknowledgement will be sent and that packet will be recovered. So then we have the padding, and then we have the ping frame. Ping frame is to keep the collection alive, and then we have the new token frame. I will discuss it in 1 RTT and 0 RTT compare. Okay, so as you can see, I have successfully captured the QUIC packets. So this is you remember that this is my machine's IP, and then we have the destination, which is 8.8.8.8, which is the Google server's IP. So here we can see it is using the QUIC protocol, and inside the QUIC protocol, it is based on the UDP. So this is we know about the UDP. It uses source code, destination port, along with timestamps. So here let's talk about QUIC. We have different types of frames over here. You can see ping, crypto, padding, crypto, and then we also have stream frame. But in this particular packet, it is querying the Google server's IP. So in this we are having the crypto. This crypto contains the certificates TLS for proper connection of TLS version 1.3. So it is done in just one RTT. So let's talk about what is one RTT and what is zero RTT. So the one RTT contains the connection setup and security, such as we can see in the crypto frame. These are all the security that is being embedded in just one round trip time. It only takes one round trip time to have the connection setup along with the security. But also it is also optional that we if we want to send any data in only the first round trip time. But over here, we are not having any data because of the absence of stream frame. But we'll discuss about the stream frame as well, how it is structured. So in this one RTT, the whole connection is set it up. But we have also observed that what is zero RTT. Okay, so let's talk about the zero RTT. Over here, you can see the new token frame. It is the basically main cause of how we are using the zero RTT. Suppose if there's any initial connection, it usually begins with the one RTT because if we want to establish any connection, we just need one RTT to get it secured and have all the settings up to date. So after that, the most of the servers release tokens, and that token is being sent to the client side. So what is happening is QUIC stores that token in the new token frame so that in future if we want to establish the connection again, so the QUIC just passes their new token frame to the server side, so the server matches that new token and quickly establish without any use of RTT. So that's why it is said that QUIC also uses zero RTT. Okay, so now we are comparing a TCP packet with the QUIC packet. So here you can see I have selected a TCP packet. So in this packet, we can see that this one is the packet. This IP is also of Google server's IP. So here you can see it is using the transmission. It is using the source port, destination port, and then the IP addresses. Along with that, we have acknowledgement number, sequence number of a packet, and along with that, we have the sequence. We have checksum. We have window. Then we have the flags for syn, act, push, finish. So this is the overall representation of how a TCP is represented. So let's take a quick look again at the QUIC packet. So here we can see the destination connection ID, source connection ID. This is that is how it overcomes the migration part as compared to the TCP. Whenever the IP changes, it completely relies on the connection ID to overcome the migration problem. So here you can see different frames, token length, payload, which is the data, and then and it operates on the UDP protocol over the UDP, which is having source port, destination port, checksum, timestamps. So this was the QUIC packet capture. So, in a nutshell, this is how we have compared the context of the HTTP2 with the HTTP3, which is the QUIC. It has reduced latency, no head of the line blocking, seamless mobility through connection IDs. Then we have the built-in security because in the first packet transfer, it is integrated with the TLS 1.3 security. It has better performance due to multiplexing because it can multiplex streams up to 2 to the power 62 independent streams per connection. So there's a no chance of head of the line blocking at such a scale. So you can see this is what we have analyzed in this video about the QUIC TCP. So it is UDP based and it is connection oriented. However, among the QUIC TCP and UDP, UDP is the fastest, but it is not secure. TCP is really reliable, secure, but it is slow. QUIC is reliable and fast, along with various benefits like migration, multiplexing, HOL blocking as well. So let's look upon the some extent of disadvantages, but there are mitigations to overcome those disadvantages. Like some UDP issues firewall that blocks the UDP communication, so QUIC cannot be established. Moreover, it uses high CPU use. It runs in a user space, and also there's a debugging difficulty because encryption is harder to expect with standard tools. Lastly, talking about the threats, there is the one common threat which is the UDP application attack, in which an attacker can spoof the client IP and can cause the server to send a large amount of initial replies. So in order to tackle that, initial packets are being padded to at least 1200 bytes. We have seen that padding frame, it is responsible for that only. And then we have the zero RTT replay attacks in which is sent in zero RTT packet, which can be replayed by an attacker. So it has been made idempotent only. Along with that, there are some static connection IDs that could be used to track users across the network changes. But for that, we are using frequent connection ID rotation, which makes the QUIC more reliable. So this was the whole QUIC detailed research. So thank you for watching.